Hello, my name is James Ahrens, and today I'll present technology trends and challenges for large-scale scientific visualization. By way of introduction, I wrote this article to describe what was next for scientific visualization. The talk is based on a Visualization Viewpoints article. I was inspired to write this article based on Chris Johnson's CG&A article in 2004 entitled Top Scientific Visualization Research Problems. My goal in my work was not a complete list of problems, but rather to focus on the implications of technology trends on science and scientific visualization. It's a great time. We see signposts like the delivery of exascale supercomputers, the explosion of high-resolution sensors, and a revolution in artificial intelligence. Technology trends, computational advances that have a significant impact on our field, I will identify in this talk. And then the challenges or opportunities that result from this trend, I will also try and highlight in terms of what our next set of challenges are. So as we all know, Moore's Law has been just an amazing, phenomenal growth in the number of transistors on a microchip. It has sort of continuously doubled approximately every 18 to 24 months. And from a science perspective, this has led to faster processors that can help us do scientific simulation and process data extremely quickly, as well as a revolution in sensor technology with sensors achieving high resolution and better dynamic range over time. Jim Gray pointed out there's scientific paradigms. So as you look at this table, you know, the empirical scientific paradigm occurred thousands of years ago, and it was, think of experiments describing natural phenomenons. Theoretical techniques came in the last few hundred years. This is things like mathematical techniques, including the use of models and generalization. But really, the computing revolution has supported computational paradigms and more recently data-driven paradigms. And these computational paradigms support simulation of complex phenomenon, and data-driven paradigms allow us to unify these experimental simulation theoretical results. The implications of this massive computing and data on science is that science endeavors will, whether simulation-based or experimental, will be high resolution. And in addition, these endeavors will have ensembles of simulations and experimental results. And this is really good for the scientific method because we will have lots of evidence from multiple simulations and multiple experiments that will tell us about our scientific knowledge. So critical, once you have many simulation ensembles and experimental ensembles, is you need scientific approaches of verification. That is the process of checking whether simulations or experiment meet their design requirements. And validation, the most important activity, where you check whether simulation match real-world experimental results. As a key part of the paper, I made a representation of the levels of the modern scientific process, starting with the most concrete levels with the data element level at the bottom and going up to the validation level at the top. I will go through this chart in more detail on the next two slides. So let's take a look. So at the traditional levels of the scientific process, we'll start with the data element level. These are things like scalars, vectors, tensors, and they represent a single element. And so a lot of our work in scientific visualization is focused here. We have very effective scalar and vector field visualization techniques. And we really, our challenges are these more complex data elements such as tensors or functions. Moving up a level, we get to the notion of a grid that, there's a connection between these data elements. And so just following the chart here, the three columns, okay, the first three columns after the labels on the left represent different simulation types. And then you can also imagine different experimental types as well. That's the next three columns. Our goal at the grid level is to visually understand complex grid types such as adaptive meshes, unstructured grids, and high order elements. We've seen as Moore's law allows a lot more cycles. You can have a lot more complex elements in your grids. From a systems challenge, a system is the ability to you sort of put all the things together. You have your grids, your data, your input data, your input decks. These produce particular output decks. You can think of that in a simulation sense, or you can think of that in an experimental sense. I set up a specific scientific apparatus and sensor, and I bring those together, and I run an experiment. So at this level, these are traditionally what has been done in scientific simulation. If you think about it, we'll have a climate model. We'll look at the climate model evolve and study the multivariate and temporal nature of the results. In addition, we want to start thinking about the relationship of what is the input deck, how does the input deck change the outputs. Okay, whoops, wrong way. So now, in terms of the modern scientific process, we're starting to see ensembles of results. So not just one simulation, but up to thousands of simulations being run using different approaches and different solvers and different input decks. And so when you have an ensemble level, the challenge is to understand both the set and the relationship between the elements in the set. So we really understand, I've got a large parameter study of a simulation or an experiment. What does that tell me about the scientific field? Next, as I pointed out on the last slide, verification is this process of checking whether the simulations meet their design requirements or if the experiments are meeting their design requirements. That's an important step. What's interesting at this level is now you start thinking about ensembles of ensembles. I've run a set of simulation experiments, or I've run a set of experiments, and then I put all those together and make sure the apparatus is working correctly. So for experiments, it might be like an accelerator facility. For simulations, it might be different suites of ensembles with, say, different grid types running on the same type of simulation, like a climate model. Finally, we advance up to validation, which takes both ensembles from the simulation side and compares them to the ensembles from the experimental side. And so you're really going to need techniques that work on high dimensional data, comparison methods, and representation of properties of these ensembles, such as uncertainty. And I really see this getting into a merging of information and scientific visualization techniques for success. Another thing to point out is we've gone up in these columns on the simulation side and on the experimental side. You can imagine if you find differences that you might want to dive all the way back down to look at particular runs or even particular data elements. And you're going to want to traverse this hierarchy of levels up and down to sort of understand both things at this macro level and then at a micro level. Okay. A second technology trend is that memory and storage devices have improved at a much slower rate than processors. And so this is a real challenge because our ability to store data on supercomputers is order of magnitude slower than our ability to generate data. So our challenge is how to quickly and significantly reduce the data without reducing its usefulness. This has led to a bunch of techniques, including data reduction at the data source. So things like edge computing, in situ vision analysis, and compression. We'd like to look and explore analysis and visualization techniques that preserve particular data properties. Topology is a good example, and there's been a lot of good work here. And automation techniques, because when you're having data reduction at the data source, you typically don't have a human involved. So you're making decisions, automated decisions in real time without human intervention. Because of physical limitations in chip architecture, we expect that there'll be a deceleration in Moore's law. So what the industry is doing is designing custom chips. So things like ray tracing and machine learning chips are on the horizon right now. And our challenge is how can we best take advantage of these custom chips for visualization? For example, how can we represent visualization algorithms on a machine learning architecture? In the scientific visualization community, we've had a lot of success with this. For example, we've ported our visualization algorithms to GPUs. This is the VTK work led by Ken Moreland. And that's a really good example of taking advantage of custom hardware to accelerate the scientific visualization process. Finally, another technology trend is the emergence of new successful machine learning techniques. And again, we'd like to understand how we can take advantage of these advances in machine learning to solve scientific visualization problems. The first challenge is visualization for understanding scientific machine learning. This is important because as machine learning is used in scientific endeavors, it strengthens the need for strong verification and validation of the scientific results. I believe that this notion of because machine learning depends on ensembles, it's synergistic with the approach that we described earlier of scientific verification and validation challenges. So if we solve those challenges, we can solve some machine learning challenges. The second challenge is using machine learning for scientific visualization. And so can we use machine learning techniques to help us with this? I imagine we can, particularly when we're thinking about large-scale scientific data and doing emulators and finding simulating results where we may not have all the data. In terms of interfacing and understanding what the humans are doing or how they might help us with automation, it's not really clear that we have the amount of data or the quality of data that we need to do this. So in conclusion, the technology trends, including extremely capable supercomputers and advances in machine learning, offer a bright future for researchers and practitioners to address the upcoming challenges in scientific visualization. Thank you.